Welcome to this lecture in which we will present an example on GPC law. We will present an example, present Scilab code, and we will show how the control law can be represented through 2DOF. Here is the example that we already studied. This is taken from Camacho's book. The reference is given in the textbook. We have AB entries. On dividing 1 by A delta, we get this EJ, FJ polynomials, and we defined GJ as EJ into B. We have taken NY and NU to be 3, the prediction horizon and the control horizon, NY and NU respectively as 3. We already showed in the last video the values of E's and F's, and then EJ into B. Then we put them in the form of this matrix and recall that we flipped the entries here. So 0.4 comes here, 1.32 comes here. Similarly here, it starts at 2.05, 6, then 1.32, then 0.4 as given here, and so on. We have already seen this. In general, this is not square. Here we have it as square because we have taken NU equals NY. Alright, from the same equations we get H1, and we see this to be the last entries, namely 0.6, 1.08 and so on. From F entries we get these equations and we stack them up to arrive at H2. I would want you to do this exercise, but you don't have to submit it. Repeat this for N or NY equals 4, but let NU equals NY minus 1, that is equal to 3. That is, the prediction horizon is 4, control horizon is only 3. You can check your results with the Scilab code that I am going to show shortly. This is the GPC law we arrived at in the previous video, and we used this variable called K, and we want to implement only the first row, that is only the delta U n term. Okay, let's display the calculations once again, and this is the control law U underscore in terms of K. I have multiplied out, I have got this expression, and I got KH1 and KH2. The control law is given by the first line. So let's do that, that is delta U n term. So you can see that it is given by the first row multiplied by this reference signal. So we have 0.1334 into R of n plus 1, 0.2864 into R of n plus 2 and so on. Then KH1 into U volt. So we have to take only the first term. So this is 0.6045. Because it is U volt, use the previous one. You have to see the definition of U volt in a previous video. We have a minus sign here, so that comes here. Similarly, we get for KH2 into Y volt, we get these two terms corresponding to these two entries in the first row of KH2. Here is the Scilab code given, GPC underscore weight dot SCE, and that calls GPC underscore n dot SCI. Here is the output from the Scilab code, KH2, KH1 and K. The same Scilab code echoes these values also. Recall our 2DOF controller in terms of R, SC and TC, and here is the control law we derived when we worked out by hand, shown 3 slides ago. And note that the output from the Scilab code is in agreement with the expression here. you can see these 4 terms of TC are nothing but the 4 terms that we already used. You can see 0.1334 here, similarly 0.0022 with a minus sign, and this is nothing but TC. Remember, in our TDOF, TC multiplies the reference signal R, and then minus 0.6045 into delta U n minus 1, it comes here. Notice that delta U term is here, here also it is present. So if I take this to the left hand side, then it will become 1 plus 0.6045 Z inverse into delta U. So that is the term given by R here. So I have this, and then these two correspond to the SC terms that multiply plant output Y. So the Scilab calculations are in agreement with what we predicted. To conclude, we showed how to get the GPC law in 2DOF framework. We have to choose the reference signal R to vary slowly. For example, we could choose R as the response of a first order system. A similar response was shown in the schematic in the previous video. Any of the XCOS files already created and used in the previous videos can be used for simulation using this 2DOF control law. So we got a 2DOF controller out of GPC control law as well. I would want you to try out the Scilab code. I would want you to verify the efficacy of this control law using XCOS files already given to you. I would want you to change NU, NY, rho and so on, and try the effect of all these tuning parameters. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.